Whenever you're ready.
Okay, great. Good morning, everyone. This is Elizabeth speaking to you from the Ether. And today, myself and Ching will be talking to you about two projects nested within a collaborative effort to use simulation to assess and reduce conflicts between drivers and bicyclists. Collaborators include researchers at the University of Iowa, UMass Amherst, and University of Central Florida. If you head to that next slide for me, thanks. For my portion of the presentation, I will focus on the use of protected bike intersections as a means of reducing right hook crashes. So you can head to that next slide for me. Great. The adoption of separate bicycle lanes is on the rise. It isn't surprising given the advantages this provides to riders' overall safety. A rider that is separated from traffic is less likely to be involved in a crash. This increased sense of safety is also responsible for increases in bicycle ridership, with more Americans choosing to bicycle for exercise, for fun, as well as for a means to commute to and from work. However, crash risk increases when bicyclists and vehicles interact when they come back together at intersections. Due to a prolonged period of separation, drivers may be less likely to anticipate and scan for the presence of bicycles and vice versa. This risk is especially concerning when considering right hook crashes. So as you'll see on my next slide, here we have an example of biking infrastructure that separates cyclists from motor vehicles. However, the risk for a right hook crash is high. The driver might not be looking for bicyclists, and due to the proximity of the bike lane to the roadway, the driver could easily collide with the bicyclist. On my next slide, we have what is known as a protected bicycle intersection. Like the previous slide, the bike lane is separate from the roadway. However, this type of intersection differs from the first in several key ways. First, the section of roadway nearest the bike lane is reserved for parking, further separating roadway traffic from cyclists. Additionally, in the front of the parking lane is an extended curb area. Now, as you can see, the greater distance between the driver and the bicyclist is designed to create visual angles that make it easier for the driver and rider to see one another, as well as give the driver and rider more time to react before a collision. So if you'll head to, so our goal in this research is to systematically test whether protected bike intersections reduce the likelihood of bicycle-vehicle conflicts involving right hook turns, both by observing driver and bicyclist behavior. You can head to that next one. So we plan to compare separated protected intersections to non-protected intersections. At the University of Iowa, we'll use our cave-like immersive bicycling simulator to study how bicyclists respond to virtual cars making right hook turns. So does the protected intersection give bicyclists enough time to perceive and react to a car making a right turn? UMass will use their driving simulator to study drivers' response to cyclists when making right hook turns. Can drivers better perceive cyclists when in protected intersections? And how does this change driver behavior? If you'll head to the, So in thinking about how best to approach this collaborative project, we would like to make the bicyclist and driver experiments as similar as possible in order to make direct comparisons. Looking ahead, this could present some challenges related to software differences between the two systems. And when in thinking of events presented in the simulation, it's important to consider if right hook turns should appear as a one-time surprise event or if they can occur multiple times throughout the ride or drive. Further, timing of such events is going to be critical and also can present a unique set of challenges for both simulators. Measures will likely include a categorical measure of collision or crash, as well as continuous measures of speed, braking or slowing at the intersection in response to the event. Gaze direction will also be critical in determining the effect a protected intersection has on providing bicyclists and drivers more time to perceive and react to one another. So now I'm going to turn it over to our colleague from Central Florida. This concludes the UMass U-Iowa collaboration of this broader project. So we'll hold questions and comments until the end, but we are particularly interested in any input that you may have about the task characteristics. Thanks.
Thanks, Elizabeth.
Thank you, Elizabeth. Hello. This is Chin Chai from UCF. So in the following presentation, I would like to introduce you about our research for the bicycle safety from the UCF. So our project is an assessment of traffic safety between drivers and bicyclists based on the roadway cross-sectional designs and countermeasures with simulation. Next slide, please. So in our project, we have two objectives. So the first one is to conduct a comprehensive safety analysis to explore the safety effects of roadway geometric cross-section designs on mixed traffic condition. So for that objective, we would like to develop SPF and CMF for the roadway countermeasures based on the data availability to identify applicable treatments such as the add backlands on the segment and add the bike box for the intersections and identify the hotspot. And for the second objective, we would like to develop a micro simulation based on the identified hotspot and test different treatments identified from the first objective. So different from the real-time quest, uh, uh, from the data analysis, we can compare the result from the different scenarios. So this slide present our preliminary studies for the CMF to assess safety effects of adding bike lanes for open arterials. For that, we connected the 227 segments which added bike lanes during the year from 2006 to 2009, and we collect data from the 2003 for 2005 as a before and the year 2010 to 2012 as an after study. So actually, both before after study and the cross-sectional study has been conducted to estimate the CMF. So from that, the table, you can see that actually the safety effects by adding bike lane along the segment is positive. So you can see all the CMF with significant less than 1. And also you can see adding bike lane is more effective in reducing bike crashes because it compared with the total crashes, it has a lower CMF values. Next slide, please. So this is the following research task. Definitely, we will identify more applicable treatments such as the adding bike box at the intersection and develop a CMF and SPF. So then in that case, the applicable treatment can be identified based on the comprehensive safety analysis, and followed up, we will like to conduct the micro simulation experiment. So that the preliminary study of the adding bike lanes will be evaluated in the micro simulation. So in that case, we can test different scenarios for the treatment and compare the result with the comprehensive study, which is based on the real data. So in that case, we can see the two applicable, different studies can support each other. So this is the next slide, please. So this is our project schedule. We plan to finish it in the 15 months. That's it. Any questions? So I would like to answer.
All right, thank you. We do have a couple questions coming in, it looks like. So we have time for one question. Where was the data from for the CMF study?
The data is collected from the segment in the urban area from the Florida. So we would like the collected from the FDOT provider of this data.
So continuation of the first question, did that SBF account for the bicycle volumes as well?
No, we only included the AADT from the segment, but we consider some social demographic uh, social demographic values such as the population as surrogate measures for the bike volumes.
Okay, well, thank you both for presenting about this project. We do have one more person typing. We'll see if what that question is, but we are going to get ready for this next presentation. It's multimodal distributed simulation combining cars, bicyclists, and pedestrians. I believe that presenter is in the Hank lab, so I will just leave them um, presenters. One last question. Is it possible to give your credentials?
Contact.
So feel free to leave your email in the comment box after your presentation if you'd like, and then other people can contact you if any follow-up questions. So thank you for that question.
Okay, thank you.
Okay. And is Yuan ready in the Hank
Yes.
lab?
Yeah, you can hear me, right?
Yep, I can hear you. 1 second here. Let me get your presentation pulled up, and then we can get started.
Thank you. Yep. Are we good to go?
Yep, you are good to go. Sorry about that. Let me get it full screen again, but you can begin whenever you are ready.
Okay. Good morning. This is Yuan from the Hank Lab in University of Iowa, and today I'll be presenting a new project between our school, Wisconsin Medicine, and UMass. And we are working on trying to connect our simulators together. Next, please. So the motivation is really about how to minimize crashes. As we all know in this group that the driving, bicycling, pedestrian behaviors are studied separately in different simulators. Next, please. But also in this whole situation, the interaction between different drivers, bicyclists, and pedestrians are also very important. Next, please. So to study the interaction, we propose connecting our simulators together, like you see in a graph. Next, please. Two people will be sharing a virtual environment and they can interact with each other. And in the future, we're also trying to look at a warning system that will minimize the crash risk. Next, please. So we're trying to connect simulators in 3 schools in this new project, and we're thinking about pedestrian, bike, as driving simulators. Next, please. So currently, the UW Medicine is working on their Unity-based driving simulator, and they're planning to integrate a driving simulator into the loop. And UMass already have 2 RTI driving simulators integrated, and they're currently running an experiment looking at multiple vehicle crashes and mitigation crossing mechanisms. And also at the same time, they're working on integrating 2 other Unity-based driving simulators into their existing 2 connected RTI simulators. This will provide a very good foundation in order to connect simulators across different schools. And in our university, we have two large screen simulators. As you can see in the graph, it can be configured as pedestrian or bike simulator. So in this simulator, in this talk, I will just use a connected pedestrian simulation as an example. Next, please. So for connecting Unity programs, we can use two types of network connections. The first one is between multiple Unity simulations. And within Unity, we can use high-level API or low-level API. The high-level API is more convenient and is very good for our use. And we have a prototype working in the Hank lab in UI. So because the high-level API can manage all the moving objects life cycle and control all the performance and the synchronization, so it's fast to implement and has a great performance. And also, the Unity program can be connected to other type of simulators. Next, please. Yeah, in that way, Unity supports 3 different languages, C#, Java, and another language called Bool, which is kind of like Python. And if we want to connect Unity to other existing simulators, we need to just use the typical UDP or TCP connections and write all the synchronization and network performance by ourselves. This will be very useful in the sense that if there are already complex traffic server programmed, we don't need to reprogram in the Unity. And next, please. So in our lab, the pedestrian simulator, we use Unity as the program to do our simulation, and we have an OptiTrack system, which is tracking software that will track the people's movements. And the tracking data, next please. The tracking data will be fed into the Unity application. Next, please. And the Unity application will draw different angle correct images on the different walls of the cave. Next, please. And as you can see, it has 3 walls and a floor, and then it's currently running in stereo, so that way you can see the animated character showing up actually inside the volume. Next, please. This is an abstract view of the pedestrian simulator. This is me and Elizabeth in 2 rooms and in 2 caves. So next, please. The general goal is to have Elizabeth movement in the first simulator, the client A, being passed over to the client B, and my movement from the client B passed over to client A. And we need to, the tracking information will be used to drive our avatars around so we can interact with each other via avatars. And also next, please. Then there will be a traffic generator somewhere in a server to provide the traffic information and give us the cars. Next, please. And this is a more close view in the system graph of the high-level API. Next, please. So as you can see, we have 2 tracking systems in 2 rooms and 2 Unities running in 2 rooms. And one of the Unity will be configured as host, which is one application that contains the server program and client program. Next, please. So the tracking information from the first person will be sent into the local client and do some calculation for my anchor site that will be better suited to move the avatar around. And then the information will be passed over to the next room, the Unity B, via a server application, and then this anchor site will be used to drive the avatar around that represent person A. Next, please. And the traffic will be directly controlled by the server program and updated to all the clients. Next, please. And next. And similarly, we just need to pass the schedule anchor of the person B to the server and then to the client A. So all the information are minimum, so we don't need to pass the models around. It's just ID, position, or orientation of the trackers or the cars. Next, please. So there are challenges to make the unit networking between different platforms working. For example, it's a steep learning curve for new students. They need to know one of the simulation languages good enough to program the networking APIs and the general Unity application. We use C# in the Hank lab, but I would assume other labs might use different languages. And then, but the good news is there are a lot of learning resources for the Unity. There are a good community online, and there are a lot of YouTube videos. Next, please. But this remote collaboration has its unique challenges. So we need to figure out a way to establish a network protocol between 3 different simulators or more in 3 different schools. And then all the students need to work very closely at the same time, trying to do remote testing, debugging, and also share the big Unity project and for every step of debugging. As you all know, the simulation project is very big. It has all the models and all the textures, so it's kind of a challenging job to do. And then also, we need to figure out if the network speed is good enough to support real-time simulation. We need to, at the very beginning, try to design the simulators passing minimal network traffic. And also, when we get a demo running, we need to figure out how to do a loop time testing. And if the network is not performing very well, we need to figure out a way to compensate the delay in the local applications. Next, please. And also run an experiment in previous slides, please. Thank you. Yeah, so also running the experiment remotely is challenging. So currently we're trying to figure out a way to run experiment just in our school between the 2 Hank caves. It's already required collaboration between the 2 experimenters because we're planning to kind of talk to each other via phone or a speaker so we can synchronize the experiment running. Next, please. There are several similarities between different simulators, which make the job possible to do. For example, we all need a central server that sends traffic over. And also, even though the pedestrian, bike, and car simulator are different, but the information that can be passed on network are sort of similar. For example, the pedestrian simulators is passing ID, position orientation of every tracker, and the bike is a position orientation of a bike and a position orientation of a car. So the general structure is similar, but there are also challenges trying to connect different types of simulators together or even the same types. So in the Hank lab, we're working on connected pedestrian simulators or bike simulators. For example, if we want to connect 2 pedestrian simulators, we need to make sure the reduced marker tracking system works in 2 realms and the information passed in the 2 realms are slightly more complex because we want to pass a tree of all the markers. Next, please. And when we want to connect different simulators, the situation is a little bit more complex because if we want to use one code base for both simulators, which is the most convenient way to do in high-level API Unity connection, we need to sort of make this one project working both as pedestrian and a bike simulator. This means this whole coding will require more control logic. And also we need to figure out how to do the pedestrian relocation and re-encounter, which is a problem that we always talks about when we try to connect pedestrians to either driving or bike simulation, because we want to make sure they encounter each other frequently, and also probably we need to mix in different agents to give some surprising factor. Next one. Thank you so much. And questions?
Okay, so we have time for one question here quick. And our next presentation will be enhancing school zone and school bus safety. That'll be from UCF.
Thank you. So no questions?
I think that will be everything. Thank you, Jan.
Thank you.
Okay, so I did make that UCF Lee a presenter. Feel free to connect your mic at the top of the window. And I will be getting your presentation pulled up.
Okay, sure. Hey, I'm Muta Saad from the University of Central Florida. So you can hear me all right?
Yep, we can hear you.
Okay, good.
Okay, so I'm gonna start the screen share and then feel free to get started once it's pulled up.
Okay. Okay, thank you. Uh, so good morning, everyone. I'm Muta Saad from University of Central Florida, UCF. I will present the research project of the Enhancing School Zone and School Bus Safety. So next, please. So generally, traffic crashes with involving the school-age children are a serious concern, and there has been an increasing in the number of school-age pedestrians and cyclists injured and killed throughout the years. So mainly our problem here is the school zone area because it has lots of the conflict between vehicles and rear-end crashes. So we have here three research questions. First one is for the best countermeasure to maximize the driver speed limit compliance rate in school zones. Second is for the optimal roadway environment to increase traffic safety in school zones. And finally, the third one is the best school path design to improve driver behavior. So generally, we want to improve the speed limit compliance and the roadway environment, including the geometric design. And also, we need to improve to get the best design of the path and for the stop signs. So next, please. So that's why we have three objects here to account for our research questions. First one is for analyzing the driver behavior for the reduced speed limit in school zones and the countermeasure. Second one is for investigating the impact of geometric design of the roadway and the number of driveways on safety in school zone. And finally, the exploring the driver's reaction to various designs of the school passes and the stop signs. So our first objective is for the driving behavior for reducing the speed limit in the school zone. So generally in the school zones, most of the states set a lower speed limit as specific time period to protect children from severe crashes. However, drivers often don't comply with these speed limits. So mainly, you will find that drivers can suddenly change their speeds from around, for example, 35 miles per hour to 15 miles per hour from the regular section to the school zone sections. So as we see in the figures, some devices like the flashing beacons and the dynamic speed display can be applied to increase the speed compliance, as mentioned before in the previous studies. So in our research project, we will apply two simulation techniques. First one is the driving simulator experiment here in UCF. So that will be applied for investigating the countermeasure for school zones that can increase the number of drivers complying with the speed limits. For example, the flashing beacon, the pavement marking, and the two-step speed reduction. The two-step speed reduction will be explained in the next slide. For the second one will be the micro simulation experiment. So for the school zones, it's required drivers suddenly reduce their speed, like for example, as we mentioned before, from 35 miles per hour to 15 miles per hour. So that can cause a conflict between the vehicles and also can lead to a rear-end crashes. So an additional speed limit between the regular and school zone section will be added. As we said, that's the two-step speed reduction. So this micro simulation part will be for quantifying several measurements for driving behavior, like the time to collision, the TTC, the conflict frequency, the deceleration rate, etc. So the following figure is for explaining the two-step speed reduction. For the upper figure, we can find the vehicle suddenly stop from or reducing their speed from 35 miles per hour to 15 miles per hour. So that can lead to conflict between vehicles and can lead to the rear-end crashes. So what we plan to do is making like transition zone between the regular zone and the school zone. So the vehicle can reduce their speed from 35 miles per hour to 25 miles per hour, and finally to in the school zone in the 15 miles per hour. So that can improve the safety, and we wanted to test what will be affecting for the conflict and for the crashes. So for our second objective is for investigating the effects of the geometric design of the roadway and the driveway of on the safety at school zones. So at that bar we will use just the micro simulation. So we wanted to examine the improvement of the roadway environments for the geometric design, like increasing shoulder width, minimizing the number of roadways, etc. So we want to know and to test these factors, how they affect the traffic safety at the school zones. And then we will see the actual crash data, and we will explore the actual crash data and compare it with the micro simulation results as validation for the micro simulation network. Our third objective is for exploring driver reaction to various designs of school buses and stop signs. So generally, driver must stop upon approaching any school bus that display its flashing red lights and has its stop sign extended. So some drivers may react more quickly, and on the other side, other driver may take more time to stop for a school bus. So in that objective, we will use the driving simulator in UCF for investigating how vehicle type is school bus design, like the color of the bus, the length of the extending stop arm, the stop sign size, as we see here in these figures. And also we need to explore the personal characteristics, for example, the age, gender, driving experience, etc. And we need to test and explore how these factors will impact the driving behavior, like the reaction time, the driving rate, the time to collision to TTC, and conflict frequency, etc. So for our project, we have two phases. First phase is mainly for the literature review, data collection, and for the micro simulation part, including the construction of the network, calibration and validation, and preparing for the scenarios and testing the scenarios and generating the result and the conclusion. This part will take around 12 months. For the second phase, it will be mainly for the driving simulator part, for the experimental design, for building scenarios, recruiting subjects, and conducting the experiment, and lastly for generating the results and writing the conclusion. This phase also will take around 12 months. So thank you. Any questions?
Okay, so we'll open the chat box up for one or two questions, if there are any. I don't know if you saw the chat, but there is a bus safety belt summit in Washington, D.C. on October 26th, so that might be of interest to you.
Exactly. So
Okay.
thank you, Mike, Mr. Mike. Thank you.
I guess I have a quick question. How do you think that or how much effect do you think the color of the bus will have on um, the I guess, reaction? I know you mentioned that in your experimental plan.
Exactly.
Just might be interesting to see a blue school bus driving down the road.
So we will test that using the driving simulator, and we'll see, because, like, for example, now it's just the yellow bus, so we need to see how when we extend this to different cars, like 4 or 5 cars, how, like, using also the yellow fluorescent instead of the yellow. So we need to examine this in the driving simulator to see how this will affect the driving behavior itself.
Okay, thank you.
Thank you.
So we are going to move on to the next presentation. We actually have the researcher here at NADS with me, so I'm gonna pull it up and then turn the mic over to him. So if you can give me 1 second. So I have it unmuted. Get it started here. And then you can just click on the arrows to go to next.
So everyone can hear me right now?
Get a little more in front of that mic, and then you should be good.
Can everyone hear me? Hello, my name is Omid. So in this presentation, we want to study the driver state, see if we can detect it and how it influences automated driving. So what we want to do is define readiness in vehicle automation, and there are two areas that we want to study: partial driving automation, conditional driving automation, and how they cross over, and especially within the dynamic driving task. So is the driver taking over without any feedback, or is there some kind of feedback for the user? So this relates to the transfer of control within automated vehicles. As you can see from the table below, when the transfer of control is from lower to higher, we expect pressing a button and having the vehicle take control, and what we don't expect is collision avoidance. So what we want to look at is the opposite, from transfer of control from higher to lower, when the human has to take control and grab the wheel, and we want to avoid automation failure where there is no warning. And so this graph kind of just shows you different levels of awareness. You could be anywhere from drowsy and distracted to very vigilant, and we want to see if our driver monitoring system can help detect this. So some of the questions we want to answer is, can driver monitoring be used to categorize situational awareness? And can we use situational awareness in our driver monitoring system to modify the timing of a takeover request? This is a video of a takeover. It shows. Can we play it? So basically, it shows the takeover scenario from early Safer Sim AV study. Driver takes over request and takes back control, and we can see a period of requiring situational awareness during the takeover. So there are multiple different takeover situations we can analyze, and for example, work zone or slow lead vehicle. In more capable situations of an autonomous vehicle, there is no takeover request. For example, in a work zone, if it's less capable, perhaps provide a 10-second warning. In more urgent situations, such as a slow lead vehicle, even if the car is more capable, 10-second warning may be needed. So the way we want to set the study up is we want to have a 5-minute acclimation to the driving simulator for participants, and then a 15-minute trust building period with automation. So then the different scenarios we want to study are planned takeover requests and unexpected events where there's failure without takeover request. And so this is kind of like the series of steps we want to take for this study. So the first step is to identify situational awareness ground truth measure, and then classify that readiness, using ground truth measure. And, some of the techniques we can use are on the right side, and bullets, latent hazard detection, eyes on forward road, freeze probe technique. And then once we have classified ground truth, we want to see if we can use the monitoring system to tell us something about the ground truth that we measured previously. And more advanced applications would involve machine learning. So how does driver state influence takeover and acceptance? Well, it influences the takeover quality, takeover time, errors, stabilization, steering and lane, eye gaze, and head behaviors factor in all of this as well. So yeah. That's it. Any questions?
The question is, how do you assess ground truth?
Good question.
And we have Dr. John Gasper in here too, so he might help with this a little bit.
Yeah, so the question of ground truth is really kind of the first step in this project. So to be able to predict driver state using this driver monitoring system, we really have to first understand the true state of the driver. And that's still really kind of an open question in the area of automation. So what we mean when we mean that the driver is actually ready to take back control. So it's one of the questions we want to look at. But we can think about things like latent hazard detection. Is the driver looking at areas where we expect important information to be? So we plan to pull from different areas, different fields that have use different approaches to situation awareness. But we're working on it. It's the short answer, I guess.
Okay, any other questions? Okay, well, we will move on to this next presentation. Yina Wu from UCF is going to be discussing their project on the connected vehicles transition and market penetration. So you are still a presenter. You can go in and unmute your microphone and you should be good to go. I will get the presentation pulled up.
Hello, can you hear me?
Yep, we can hear you.
Cool. Hello, everyone. So I think I can start my presentation.
Yep, give me 1 second to start the screen share and get it pulled up, and then once I get it on the screen, you can get started.
Sure. Okay, thank you. So thank you for attending the presentation. The title of the presentation is The Impact of Connected Vehicle Market Penetration and Connectivity Level on Traffic Safety in Connected Vehicle Transition Period. I'm Ina from University of Central Florida. Next slide. Yeah. Firstly, I would like to introduce the background. The development of information and communication technologies have facilitated connected vehicle technologies in which vehicles communicate with other vehicle, roadway infrastructures, and pedestrians in real time. In this project, we define 4 different levels of connection. The first level is level 0, which do not have any connection. The second level is level 1, which only have V2I connection. The third level will have V2V connection. The fourth level will have both V2V and V2I connection. Next slide. Yeah. So there are 5 objectives in this project. The first objective is proposing strategies to help connect vehicle to avoid crash in fault condition. The second objective is using V2V and V2I information to predict the traffic patterns of conventional vehicles. The third objective is recommending the optimal connected vehicle technology and active traffic management strategies under a connected vehicle environment in fault conditions. The fourth objective is building car-following models for connected vehicle platoons. The fifth objective is recommending the number of connected vehicle platoon managed lanes under different penetration rates. So, what is connected and autonomous vehicle? The connected and autonomous vehicle, which is CAV, involves of 4 types of technologies: vehicle-to-infrastructure technology, vehicle-to-vehicle technology, vehicle-to-pedestrian technology, and autonomous vehicle technology. V2I technology enables driver to communicate with roadside equipment units. Thus, the driver could know the unobservable road condition, such as downstream congestion and speed limit on a curved section. V2V technology enables vehicles to communicate with each other. A vehicle could know the movement of the other vehicle, like speed and brake status. The V2P technology could enable drivers aware of pedestrians and avoid the potential crashes. AV technology points to the non-manual control and autonomous driving. So we can say that V2I, V2V, and V2P technology enable you to know very detailed information about your driving environment. You could communicate with the driving environment, or even have an active influence on it. Since this project will mainly use V2V and V2I technologies, I would like to introduce more about V2V and V2I. The V2I helps a driver know road conditions like downstream congestion, speed limit on a curve, signal status, stop sign, and pedestrian crosswalks. so that the driver could adjust his or her driving speed, awareness of travel route, and so on to avoid a potential crash or congestion. For V2V, it helps a driver know an unobservable present or unpredictable movement of another vehicle in pre-crash scenario, so that crash avoidance behavior could be made in advance. Take the common lane changing scenario as an example. The blind spot warning could be used when the driver wants to do lane changing. Warning message could be sent to the driver if dangerous situation may present. In this project, we want to evaluate the effect of connected vehicle technology during fog. During fog conditions, the drivers may not be able to see the front vehicle because of the reduced visibility. For example, if the front vehicle make an emergency stop during fog condition, the following vehicle may not be able to stop in time. Next, please. However, under connected vehicle environment, slow-moving vehicle head warning could be sent to the following vehicle, so the driver can be prepared to avoid potential crash. Next, please. Yeah, next slide, please. These slides show how we will simulate connected vehicle in driving simulator and micro simulation. In driving simulator, the warning can be provided to the driver through the head-up display. When the front vehicle stops suddenly, the head-up display will show a slow vehicle head warning to warn the driver about the dangerous situation. In Visum, the behavior of connected vehicle can be simulated through API. This project has two phases, where at the beginning of phase 1, we are going to conduct both driving simulator and micro simulation experiments in this phase. We will spend 8 months to conduct the driving simulator experiment, and another 8 months to conduct Visum simulation. Next slide, please. Yeah, next, please. Thank you. Any question?
So we will open the chat box up for any questions. Sue, I see you need the URL. I saw the email come in. I wasn't able to respond to it yet. Let me actually get the URL here, and I will just add this into the chat box right now, the URL for the second session. So do we have any questions for Yina? And Francis, I will make Mike the presenter. So there's the afternoon session URL. You can also find that URL in your confirmation email. And then I can also include it at the end of this morning session too, just in case we get any other questions in. I think we are down to our last couple presentations, so we might have a little longer lunch break for that virtual lunch. But we'll get started. Oh, we do have one question here, Yina.
Yes.
So Dawn Marshall asks, and she may have missed it, but what connected systems are you planning to use, or are those to be determined?
Yes. So for we have two simulations. For the driving simulator, we have the real-time update of the front vehicle speed and distance. So we are going to use this this system, and we also have the forward collision warning system in the driving simulator. And in the vSim, we are going to test the platooning strategies. You're welcome.
Okay, thank you, Yina.
Thank you.
Okay, so I'm getting that UMass presentation pulled up. And Mike or anyone from UMass, were you able to connect the microphone?
Hello? Can you hear me clearly?
Yes, we can hear you a little bit. I'll try turning my volume up. Maybe try to get the microphone a little more directed. Okay,
Sure,
it's
definitely.
Dawn
Is
says
it
it's
better
clear. I
now?
think the volume just down in my room. So let me get the PowerPoint pulled up and then you can begin. Thank you.
Okay. Thanks so much. Hello, everyone. I am Farouk. Today, I'm going to present the project that we have conceptualized and proposed in UMass Amherst, but it is not started or implemented yet. The study is on the use of traffic control devices and augmented reality. The project team at this stage at UMass includes myself, Dr. Michael Notler, Dr. Eleni Christofa, Dr. Sibi Samuel, Dr. Cole Fitzpatrick, and Francis Tainter. So, thanks so much. So we might all know that traffic control devices, or TCDs, are integral part to driver to infrastructure and vehicle to infrastructure interactions. However, if you can go to the next slide, there are a couple issues with current TCDs. One is the cost of installation and maintenance of these various TCDs that can reach to millions of dollars per year nationwide. The other issue is the non-conformation or non-perception with signage on the part of the driver that can lead to several safety problems. And by that I mean there could be some visual clutter for the signs, there could be weather-related concerns, there could be conditions of traffic that might cause non-confirmation, or simply the driver can miss the information that is presented to him or her by the sign. And then the last issue could be localization. So there might be some aspects where some part of the country might have signs in one way which is not the same on the other side of the country. As a simple example, in our part of the country, we have 5-section cluster or a doghouse signal for protected permissive left turns, while in other part they might have 5-section horizontal or vertical PPLT signals. So that's a simple example of that. So these issues that I introduced, they might brought the need for an alternative mechanism that does not have these potential problems. And considering the current advances in the state of technology, we have the potential ability to have control devices that can probably be implemented at lower cost. They could be more user-centric, and perhaps they could be more robust. So if we can go to the next slide. So the alternative mechanism that is proposed in this study is using augmented reality, or AR for that means. AR has now advanced to the point where we can deliver information from a real-world physical environment to the driver in a non-invasive manner. And the main advantage with using AR is the level of flexibility and control that is offered, which allows us to provide very specific traffic control information to the driver. However, the question here is more of what type of traffic control sign should be delivered through AR, and then how such safety critical traffic control information and what specific information can be delivered effectively to the driver using AR without causing any form of distraction or engagement related problems. So next slide, please. Thanks. To address that question, this proposed study is going to use a full-scale driving simulator for that means. The specific variables that are of interest in this study are head and eye movements of the drivers, vehicle handling measures, task engagement behaviors, and physiological parameters such as heart rate and heart rate variability as an objective measure of driver's state. And right now, one thing that we are discussing is whether or not having latent hazard anticipation aspects can be added to the design of the experiment. As an example for such a scenario, imagine if a bus is blocking a traffic control sign or a pedestrian crossing sign, which is like right before a crosswalk, or it could be other types of signs. And now, using AR, we are able to communicate the information to the vehicle that is blocked by the bus. So also, as part of this study, we are interested to investigate user preference and willingness to use that technology. And we propose using user preference survey for that means. So we can go to, yep, thanks so much. And the successful completion of this study will hopefully allow us to investigate the safety benefits of using AR to deliver traffic control messages to the user and therefore ascertain the feasibility of eventually replacing physical TCDs with AR signs. And it also can shed light on which traffic control devices can have the better potential to be delivered through AR, and on the flip side, probably which ones are not recommended to be delivered through AR. The findings of this study may lead to an improvement in traffic sign compliance, allow for easier enforcement, and hopefully fewer fixed vehicle crashes. So by that, thank you so much. And we're open to the questions if there are any.
Thank you, Faru. As she mentioned, we'll open the chat for any questions. Okay, I don't think there are any questions for this one, but thank you again for the presentation.
Thank you so much.
David Noyce mentioned, let's talk. We have completed similar work in Wisconsin. So if you have any questions or any ideas, feel free to send any questions Wisconsin's way.
Sure, that would be
That's another beneficial point of these symposiums and just UTCs in general. I mean, this collaboration effort really helps get ideas turning, gets, you know, you can talk to people and spark new ideas. So thank you for that note, David.
okay.
So we are on to our last presentation for the initial projects. Let's see here. This one is from the University of Wisconsin, Madison, and unfortunately their presenter was unable to make it at the time today. Luckily, they were able to provide a recorded video of the PowerPoint, so I am going to get that started here. And then if we have any questions at the end, hopefully David Noyce or maybe Kelvin is in here to answer any questions. Okay, so 1 second, let me get it pulled up.
My name.
Oh, 1 second here. A little technical difficulties. Hang with me here. Skip the volume.
That we will be working on under safer science.
Let me restart this quick. Thank you for your patience.
I'm a third-year graduate student at the University of Wisconsin-Madison. Today, I will present a project that we will be working on under safer science. This project title is Augmented Reality for Safer Pedestrian Vehicle Interaction. We are on the early stages of the project. Today, we are going to talk about the motivations and where we see this project moving forward. The project PI is Dr. David Noyce. As the automotive industry moves toward the car of the future, companies continue to develop cutting-edge systems that aim to make driving safer, more pleasant, and more convenient. In the future, augmented reality will play a key role in expanding the functionality of these technologies. Augmented reality cues have proven to be effective in assisting cognitive impaired elderly drivers. They also help in directing drivers' attention to roadside hazards and help decrease response times for detecting hazardous objects. Pedestrians are some of the most vulnerable users of the transportation system. Augmented reality has the potential to improve the safety of vehicle and pedestrian interactions. Bad visibility of the pedestrian is often the cause of vehicle-pedestrian accidents, along with other factors. Pedestrian recognition can reduce the number of pedestrian fatalities by warning the driver. Technology for pedestrian detection is already available. Algorithms have been developed and are capable of detecting pedestrians. These algorithms work on in-vehicle infrastructure as well as on roadside infrastructure, such as vehicle and pedestrian detecting systems. The challenge continues to be how we communicate the output of these algorithms using an augmented reality platform. Due to the vulnerability of pedestrians, this project will focus on studying augmented reality applications for vehicle-pedestrian interactions. Driving simulators have played a key role in evaluating augmented reality technologies. As technology continues to evolve, more and more augmented reality systems will need to undergo testing and evaluation. This project will be focused on how driving simulators can be used to streamline the process of augmented reality systems. A test platform for simulating in-vehicle augmented reality systems will be created. The procedures for connecting and testing these systems to outside the vehicle infrastructure, such as vehicle pedestrian detection systems, will also be established as part of the testing platform. This project includes a workforce development component by providing students with the skills to create in-vehicle warning systems and understand the design process. There is also an educational component as a result of the framework that will be created for testing augmented reality systems in the simulator. The test platform for augmented reality systems focused on communicating the presence of the pedestrians will be created using the full-scale driving simulator shown on the screen as the foundation. In the past, the driving simulator has been used to study augmented reality concepts that include virtual signs as well as virtual markings on the pavement.
There will be two main components to the test platform, a software component and a hardware component. The software component will be focused on simulating augmented reality systems that rely on the windshield or head-up display as the means for communicating with the driver. The hardware component will be focused on devices that are inside the vehicle cabin but do not rely on the windshield or any other screen to communicate a message. Students will have a unique opportunity to test augmented reality ideas that communicate the presence of pedestrians to the driver and participate in the design process of these ideas, thus reinforcing the workforce development and educational components of this project. The immediate tasks that will be started or completed in the future include continuing the literature review, building scenarios for testing the science, and performing actual tests of the scenarios. Scenarios used for testing will be created based on the literature review findings and will be flexible enough to support testing of the most promising augmented reality designs. Testing of subjects will focus on identifying the best streamlined procedures that can be repeated in the future for other types of designs. Thank you for your time. I'll be available via email to answer questions. For immediate questions, someone from our lab will be happy to answer your questions. My name is Hiba Nasruddin. I'm a third year graduate student.
Okay. Kelvin or David, who would like to be promoted to the presenter? Or if you think typing the answers would suffice, just let me know. Oh, sounds like it's Kelvin. If that doesn't work, let me know. But you are a presenter now, so you can go ahead. On the top of the window, there is your microphone icon, and you can connect your microphone.
Can you hear me?
Yep, we can.
Okay. So for the hand clap, we haven't dig that far yet into the project into that stage. We basically on the literature review process, and what we're going to do is simulate the effects of augmented reality layovers on the screen. So we're not planning on making them a part of the vehicle itself. So that's the software component, the overlay of the information. The hardware component will be creating different augmented reality systems that don't involve screens.
And David Noyes mentioned that they have not experienced that issue with previous research.